All right, hello everyone, and welcome to our fourth lesson, which is on physical and chemical changes. Today, your objective is to explain the relationship between macroscopic characteristics and bond interactions for chemical and physical processes. Chemical processes involve the breaking and forming of intramolecular bonds. Those are the actual covalent or ionic bonds that hold atoms together in a molecule or compound. When these bonds break and new bonds form, the result is a new substance with different chemical properties than what we started with. We usually notice chemical changes because they come with observable effects like heat or light being released, a color change, a gas being produced, or a solid being formed, which we call a precipitate. The example shown here on the right is a combustion of methane. In this reaction, the C to H bonds within the methane and the O to O bonds in oxygen are broken, and then new carbon to oxygen double bonds are formed in carbon dioxide, and oxygen to hydrogen single bonds are formed in water. So this rearrangement of bonds is what makes combustion a chemical change because entirely new substances are created. Here are some everyday examples of chemical changes. The key idea to remember is that a new substance is formed because chemical bonds are being broken and new bonds are being formed. So we have burning wood. That's a chemical reaction where wood reacts with oxygen to produce ash, gases, and heat. Rusting happens when iron reacts with oxygen and water to form iron oxide, which is a completely different substance. Digestion is another chemical change. The food we eat is chemically broken down into simpler molecules that our bodies can then use. We also see chemical changes when fruit rots, cakes bake, milk sours, fireworks explode, and so on and so forth. All of those, something new is being made with different properties, which would be a chemical change. Physical processes involve change in intermolecular forces, not in the actual bonds holding the atoms together. That means that the substance itself stays the same and only the spacing or arrangement of its particles change. For example, when ice melts or water boils, the hydrogen bonds between water molecules are weakened or broken, but the water molecules themselves, the H2O, remains unchanged. So in a physical change, we don't create new substance, we just observe the same substance in a different phase or form. This is why melting, freezing, boiling, and dissolving, with most cases, are classified as physical changes. So this practice problem says a student places a sample of pure metal in a crucible and heats it strongly in air. Data from the experiment are given in the table above. The final mass was determined after the sample was cooled to room temperature. Which of the following statements related to the experiment is correct? So first, let's look at our data provided. We can see that we have the mass of the empty crucible. Then we can find the mass of the sample before heating by subtracting the crucible. So if we take 14.4 minus the weight of the crucible, our original mass was 2.4 grams. Then after heating, we have a mass of 16 grams. So by subtracting the mass of the crucible, that means our sample went from 2.4 grams to 4 grams, which is telling us that the metal reacted with the air, probably oxygen, to create a metal oxide. So because it gained mass, it kind of gave us a hint that it is now a new chemical compound, in this case, most likely a metal oxide. So we know that this is a chemical change. So A says that it is a physical change. B says that it's a chemical change. C says a physical change. And then D says neither a physical or chemical change. So all signs point to B, but let's go ahead and check. The mass of the sample increased, so a chemical change occurred when bonds formed between the metal and another substance, in this case, the air, most likely oxygen. So B would be our correct answer for this problem. A student mixes 20 grams of white potassium chloride crystals with distilled water in a beaker. After the mixture was stirred, no crystals are visible and the solution is clear. After several days, all of the water evaporates and white crystals are found in the beaker. Which of the following pieces of experimental evidence would best help the student to confirm that a new compound had not been made and that only a physical change occurred? So we see we have a ionic salt that has potassium in it, which means we know that it is soluble in water. And when it was dissolved in water, all of the crystals were gone and the solution was clear. However, after several days, all of the water evaporated and it only left the crystals behind, which is telling us that this was just a physical change where the potassium ions and chloride ions dissolved in the water and were free floating, but when all the water was gone, it went right back into its ionic solid state. So that was a physical change. So for this one, if we wanted to ensure that it was indeed a physical change, you could weigh the white crystals afterwards, and if they were the same mass, then that would confirm that it was a physical change. So D would be your answer here. All right, and then our last question says the table above summarizes data given to a student to evaluate the type of change that took place when substance X was mixed with water. The student claimed that the data did not provide enough evidence to determine whether a chemical or physical change took place and that additional tests were needed. Which of the following identifies the best way to gather evidence to support the type of change that occurred when water and X were mixed? So first, let's look at just the substance X and try to figure out what it is. So we're given that its appearance is white and a crystalline solid, and it also has a very high boiling point, which means it takes a lot of energy to break those bonds, whatever they are. So these two pieces of information is telling me that X is most likely an ionic solid. Now, when X is dissolved in water, it's telling us that it turns to a clear, colorless liquid, which verifies that this is most likely an ionic solid that is soluble in water. So when you put that ionic solid in water, it dissolved and turned into a clear, colorless liquid with a higher boiling point than before when it was just water. So because this is just dissolving an ionic solid in water, this is most likely a physical change. So in order to double check that this is just a physical change and that ionic solid is only splitting into its substituent ions, the best way to check that is to check the electrical conductivity of X by itself, which should not conduct electricity because it's a crystalline solid, and then X inside the water because then it should conduct electricity because it has free-flowing ions. So D would be the answer here.